Hello again. Okay, as you can see, we're doing something a little bit different. Instead of having the same thing on two screens, we've got a tutorial over here and some code there. Mark is controlling the code from the back of the room. And what we're going to do is do the impossible, which is explaining Vulkan how to draw a cube in like an hour. And I think people have tried to do it in 3 hours and maybe did okay. So realistically, this is more about introducing you to a tutorial, and with the hope that you'll be so interested in it that you'll run home, put it on your computer, fire up the tutorial, start reading it, and bring up the code in a debugger and play with it and run it and learn Vulkan that way. So that's the purpose here. Just to warn you, I will be skipping a lot of things. I don't want to stand here and read it to you because that would really be bad. So it'll go fast, but I think you guys can keep up, and it'll be fun watching. It'll be like a tennis match. You guys will be looking over here and then over here, so it'll be kind of funny. So I don't have a really good feel for the what's the word, like the makeup of the audience here. So if you've ever, raise your hand if you've ever like taken a Vulkan application and stuck it in a debugger and messed around with it for a while. Okay, let's see, just for the audience, just for the record, looks like only about maybe 8 or 9 people out of 40-ish. Also demographically, I'm going to ask who develops applications and who develops like support, like infrastructure or ecosystem or tools. So if you're an application guy, okay, you can raise your hand twice too if you do both, and then tools. So it's roughly 2 to 1, maybe. All the tools guys are over here, so that's cool. Okay, so I just want to point you to the resources where you can find all this good stuff. Typically, probably the easiest way to get it is to grab the liturgy SDK. If you grab that and install it, you'll get both the tutorial and the sample code that goes along with it. Historically, we wrote the samples kind of at the same time Vulkan was coming out to try to explain to people how Vulkan works. And so they're written in an incremental way, just introducing one concept at a time. But there's no text really to go with it. As you know, engineers just love to put comments in their codes. So rather than solving that problem, we went ahead and wrote a parallel tutorial to go along with it. You can also find all this stuff online. You can actually browse the tutorial at the Lunar Exchange website. And then there's a GitHub repo that has the source code for both. And if you're a book type person, the Red Book's out, and it's really a pretty good book. The last thing I want to say before we fire up the tutorial is that, in my mind, Vulkan's another step in graphics API evolution. In OpenGL, we kind of saw the shift from a fixed function pipeline to a programmable pipeline, and that again is in response to the programmers, wanting more control over the hardware. Back in the fixed function days, if you wanted a new feature to the rendering pipeline, you had to wait for someone like SGI, if you remember that far back, or other hardware vendors to cycle their hardware. And then you had to wait for the hardware and then it would work. So now we have shaders, so that helps a lot. Vulkan, and I don't know if I like this term, but you're just taking a lot more responsibility for the drivers. You're taking on more of the responsibilities that the drivers used to do with Vulkan. And we've been kind of mentioning that all day. So I don't want to say the drivers are programmable, but you're doing more of the driver's work. And with that power comes a lot of responsibility. So, OpenGL, outside of a bad shader program, you're not supposed to be able to hang the GPU, but with Vulkan, you can't really blame the driver anymore. So we've mentioned Vulkan instances before. This is kind of your first step. And an instance is what the Vulkan API uses to store all the per application state. There's just some common usage patterns here with the API. When you create an instance, or create anything in Vulkan, any kind of object, you usually have a create info structure that goes along with it. And okay. And then also there's you can also supply your own memory allocators. And in these in these sample programs, we're not using an allocator, so this will typically be null. And then the object that comes back is usually passed back in the last parameter. And then you take a closer look at the info structure itself. Almost all of them start out with a structure type that signals, hey, this is what the structure is, partly for validation purposes, but these structures can also be chained onto an extension pointer, and you could define an extension to create info. Instance create info, and you could chain it on here and give it a different type so it can be recognized. And then the rest of the information is specific to the object you're creating. There's also an application info structure. I'll let you guys read about this, but here's where you just put in some interesting stuff about your application. And then here's the actual really simple code in the demo that just creates an instance and then quietly destroys it. So hey, you got to start someplace. We've also tried to communicate to you that when you create an instance, there could be multiple physical devices on the screen. So the next thing to do is get a list of those devices so you can decide which one to use. And getting a list of things in Vulkan also has a pattern where you call the enumerate function in this case with a null pointer for the data, and it returns back to you some kind of count, and then you resize your data structure, and then you call it again with the real pointer. And then Vulkan API fills in that information for you. Another thing I want to point out that's just very specific to the samples that accompany this tutorial is that there's a data structure called info, which is really just a big structure. It's a big pile of global data. Not the best way to write programs in today's age, but it just turns out to be effective for this sample paradigm where we introduce a concept in one sample, show it to you in the code, just like, well, I should back up maybe to show it to you in the code like right here. But then in the next sample, hey, we already learned that, so we're going to hide it. So we throw it in a function, and then you don't have to look at it again. Okay, now it's time to actually pick a device. Before you can do that, you have to decide which queue family to use. And each physical device has a list of queue family properties. And so the most important thing is you've heard some discussion on this today, is what kind of work can the queue do if it belongs to a particular family. So it can be any one of these four, or I don't know much about sparse binding actually, but at least these three are the interesting ones. And a queue can do more than one thing. It's possible for a queue to handle both graphics and compute work. So here's an example of a device that's fairly complex. It has two different queue families. One type of queue family can only do graphics, another one can only do transfer. This is kind of good news if you want to overlap transfer and graphics operations. You can do them in parallel. And then a simpler device might just have a queue family that can only do graphics and transfer. In any case, you have to decide which kind of queue you want when you create the device. And so there's some code here that goes through and it looks for a queue that has the graphics bit set, and I'm pretty sure in Vulkan that you got to have at least one queue that supports graphics, and so you should find it and not have to worry about a condition where you don't. Again, I'm going to skip very quickly here because we can't talk about everything, but basically here's the create info structure for a device, and we're giving it the queue info. And right now the extensions and the layers are null. We did the same thing for instance, and we'll come back and fill those in later. And then you create the device. Are we good so far? Thumbs up, thumbs down. Okay, excellent. All right, we talked about command buffers a lot, and everyone who's spoken about it so far today is luckily consistent with what I'm saying, so that's good. So if you want to do something like set a line width, you give it a command buffer, you say which command buffer, and then the driver will stick the opcode for setting a line width in the command buffer. This is GPU specific, so you'll never look inside of a command buffer and actually look at the memory. Instead, you're asking the driver to populate it with commands. So it sticks in an opcode and a number, which could be a parameter. It's pretty straightforward. Vulkan likes to use pools. We've got one for command buffer, and we got one for descriptor sets. I think a couple people have talked about those already. And the only thing important there is you have to specify a queue family type when you create the command pool, because you can imagine that command buffers might have different properties or formats for different types of queues. Again, this is kind of like getting into the GPU hardware, so hang on. You create a command buffer, pretty simple. I kind of wish it said get command buffers, like it would just give you one out of the pool instead of actually allocating it, but that's the way it is today. And then the only thing I want to say about using command buffers, and this is looking ahead a little bit, there's this concept of recording into a command buffer. So a command buffer has a state, and if you want to start recording into it, you call begin command buffer. Yeah. See if I can, yeah. And then once you're recording it, you can, anything you call that starts with VK command will put a command in the command buffer. And then when you're all done, you terminate the recording that way. Now, it's important to realize that when you've called end command buffer, you're not sending anything to the GPU. It's just sitting there in the command buffer, and you have to submit it later on with qsubmit, which we'll get to. Swap chain I'm going to gloss over a little bit because this is, again, something you guys can deal with on your own. But here's a picture that tries to explain what's going on. Vulkan separates the concept of the windowing system away from the core API. So instead of having core functions that create surfaces, which is essentially your window, or the swap chain, you end up using these extensions. So when you call create swap chain and say, hey, I want 3 buffers in my swap chain, maybe I'm going to do triple buffering, you just make that call with a 3, and then the implementation creates these image buffers, which are special allocations because these represent memory blocks that have to be able to be passed to the display. So they might have to be pinned in memory, or they might have to be physically contiguous or meet some other requirement. But in any case, this is one case where the object kind of takes care of allocating these things for you. And there's a lot more discussion here about what I just said. These 2 lines of code basically add the extension names when we create the instance and then when we create the device. So when you go back to create instance and create device, you would go back and modify those codes so that you activate these extensions at the time you create the instance and the device. There's a little detail here where there's another operation called present, which is the action of taking an image and getting it onto the display. There's a queue type for that, and there's some code here that makes sure that we find a queue that has both the graphics bit set and whatever, and it also supports present. And if we find one that has both, cool, we can use the same queue family index for the queues. We assign the index to both of those. Otherwise, if they're separate, we have to go and find one that supports present. It's likely that if you don't find one that supports both, there'll be 2 different queue families. One supports graphics, one supports present. That's another difference in hardware that you guys have to deal with as Vulkan programmers that the OpenGL drivers used to do for you. And then we create the swap chain. I'm not going to step through every line here, but there's just a lot of info to fill in there. You have to actually create the surface, which is pretty easy. In this case, it's 132 for Windows. Yeah, this is all real easy for you guys to figure out. If you do have different queue families for graphics and present, a little details, you have to say that they can be shared concurrently. And then finally, we create the swap chain. So this is kind of one of the things that Marcus is addressing with his C++ library, HPP, is that you go through all this stuff to get ready to call a Vulkan call, and then you have this sort of a downer at the end where you just call the function. But all that preparation is, just a lot of code you have to write, and Marcus is trying to help lessen that, so kudos to Marcus on that. All right, so even if we're triple buffered, creating the swap chain only gave us the image buffers and not a depth buffer. And since we're drawing a 3D cube, we want to use a depth buffer to do the depth sorting. And so in this case, we're actually going to create a def buffer. Instead of calling the swap chain, which create function, which created the images for us, this is an example where you have to actually create the def buffer yourself. So we do that by making an image object, and we actually allocate device memory, bind the two together, and then create an image view, which is sort of a description of what this image object is. It sort of tells us how it's going to be used. So here's the very brief code to do that. A couple highlights. Image type is a image type 2D. We're going to use a depth 16 pixel format. Width and height matches that of the window. Let's see what else is interesting. Oh, the usage is we're intending to use it as a depth and stencil attachment. So we create the image using that template. Then we actually have to allocate the memory. You can take a guess and say, well, if my image is 100 pixels by 100 pixels, that's, what is it, 10,000 pixels times 2 bytes per pixel, 4 bytes per pixel. Okay, so you can take a guess, but you'll probably get it wrong because there's usually padding and other calculations that really dictate what the real size is. So the right way to do it is to call get image memory requirements and have Vulkan tell you exactly how much memory to allocate and also what flags to use when you allocate it. So that's what's going on here with the allocation size and the type index. Memory types are really complicated, and that's another thing I want to beg to skim over right now, and you'll probably thank me later anyway. So, but it's basically, devices can have different types of memory from different pools where they allocate from, and you end up getting a type index back. So this just tells you what type index to use. Finally, you can go ahead and allocate the memory, then you bind it, and then you create the image view, which was that last step. And this just has more information about how we're using the image. So while we're creating images, we might as well create one for the uniform buffer. There we go. One thing about this cube demo that we really haven't talked about is it's pretty simple. The shader program has just one simple uniform in it, or shader variable, which is the model view projection transform. So we're going to use a uniform buffer to pass that information to the shader. And here's some you might recognize this from GL code. It's just using the GLM utilities to set up the MVP. And then the creation of the uniform buffer object is very similar to creating the def buffer, except we use different usage bit, and the size is different, of course, and that kind of thing. Again, we allocate the memory. We figure out how much to allocate. We say, hey, what do I need by calling this? Get the memory type out of it, and then go ahead and allocate the memory. And there's some more info there you can read on your own schedule. Now, what's different about the def buffer and the uniform buffer is we didn't have to look at the def buffer. It was just scratch area that the GPU uses as it renders. With the uniform buffer, we have to actually put data in it with the CPU. So in order to get host access to it, we map the memory, and oddly that's called map memory. And once it's mapped, we just memcopy the MVP into it, and we can go ahead and unmap it. Because this is a simple demo. It's just drawing once and stopping. It doesn't animate or anything fun like that, so it's pretty simple. And then finally, we have to bind the memory to the buffer object, which is what happens here. So pipeline layouts is really about descriptor set layouts and also pipeline layouts. We talked about descriptors a little bit, and those are the things in Vulkan that associate shader variables with resources, basically. And these are, I don't know, to be honest, I have a little trouble verbalizing what these mean, how to explain these to people, but I just think of them as like a descriptor is an opaque shader variable that points to resources like buffers. And so you can think of it as a pointer to a resource. And descriptors can be put into sets. And what we're doing here now is we're not actually filling in the descriptors. We're just telling Vulkan what their layout is. What is in each descriptor, how many descriptors are in a set, and stuff like that. So we do that with a descriptor set layout. And in this case, we only have a uniform buffer. So it's pretty simple. There's just one descriptor set, and then we go ahead and create a descriptor set layout. And then a pipeline layout is a list of descriptor set layouts, or contains a list of descriptor set layouts, plus some information about push constants, which we're not going to cover today because there's just so much to cover. Okay. And then if you want to understand how the shader references these descriptors, I think John K. talked about layouts a little bit, and he showed you some stuff in the shader language that defines these uniform variables and what they look like in the shader code. So for us, it looks something like this, where we just have a uniform buffer, and there's only one thing in it, and that's our 4x4 matrix. Okay. So, like I said before, Vulkan likes to use pools for some things, and like the command buffers, we have a pool for descriptors. And so we create ourselves a descriptor pool and grab a descriptor set from that pool. And this is the place where we actually fill in the descriptor with the information that we're actually writing the descriptor. We're putting the information in it that needs to be there. So we make we have a descriptor buffer info that describes what a descriptor might look like for a buffer, in this case a uniform buffer. And let me see if I can figure out how this works. All right, I've forgotten exactly how this works, but the point is that the actual information is, the sample code will do this for you if you can find it in the sample code. But we would fill in this information. The buffer would be the buffer ID of the uniform buffer, and then you'd also fill in the offset and the range, and then you'd end up pointing to the buffer info with this inside this structure of writes, and then you call update descriptor sets to actually write the data into the descriptor. So the thing to realize too here is that you just can't map a descriptor and try to write it yourself, because descriptors are going to be very specific to the device, so you have to consider them as being opaque, and that's why you have to ask the driver to do it for you with the update descriptor set command. Okay, render pass was mentioned a couple times this morning as well. The render pass, this is where Vulkan is really valuable, because this is something really valuable for Vulkan, because you get to tell Vulkan everything that's going to happen in this render pass. You get to tell it what attachments it's going to use and all the subpasses and dependencies that are important here during the rendering operation. Every render pass has to have at least one subpass, but because you give all this information to Vulkan ahead of time, it can be pretty efficient in configuring the hardware for the render pass. So we begin by creating a render pass, which is just defining it. This is another instance where we're defining something before we actually use it. Once it's defined, we're going to stick it in a command buffer by using begin render pass and end render pass. But first of all, we have to worry about creating it. I think Tobias is going to talk quite a bit about image layout transitions, and I've got a few pages here that describe, why all the memory in a device memory for a GPU isn't necessarily linear. There's other more optimal ways to read and write data to the memory for memory bandwidth efficiency. And so you have to kind of tell Vulkan exactly what layout you want these attachments to be in and how they're going to be used. So at the beginning of a render pass, the layout's undefined. And then during the subpass, which is when the rendering occurs, you want things to be optimized for GPU rendering to the color buffer. So that would be color attachment optimal. And then finally, when the render pass is complete, you want to make the buffer optimized for presenting to the display, and so your final layout is present. In a nicely architected graphics system, the engine that writes the buffer out to the display, which is kind of a display processor, would use the same format as color optimal, so there'd be no conversion happening here. In a system that's not quite so nice, it's possible that there actually might have to be a blit to go from one layout to another, which would be bad, but I think most systems today try to avoid that. Okay. So now we're going to go ahead and let me sneak ahead a little here. Yeah, we're still defining the render pass. So to do that, we have to define the attachments. So we know we have two attachments, right? We have the color buffer, which is called, yeah, this is the color buffer attachment 0, and this will be the def buffer. So info format is, unfortunately, it should be named info.color format, so it's the format of the color buffer to remind us this is the color buffer. But this information is all about the color buffer, and this is the def buffer. And then we already talked about what the layouts are from that picture that we just looked at. So there's a lot of advantages to defining these layouts as part of the render pass. You can put commands in the command buffer to do a memory barrier to do the layout transitions, and I think I'll let Tobias explain why that's not a good idea. And then there's a lot of other stuff you fill in, which are pretty much default options. Okay, the subpass stuff would be more interesting if we were doing a more complex demo, like something that did multiple, like ambient occlusion or other techniques that require multiple passes, but here it's just one subpass, so it's really simple. We just have we just define what the attachments are. Here's the color one, here's the depth one, and then the indices that we used here. This is 0 was color and 1 was depth. And then we finished filling out the subpass definition here with this data. There's a lot of nested data structures here, so it gets kind of messy. That's why the HPP stuff is pretty cool. And then finally, we can define our render pass. So we got two attachments and the subpass. Pretty simple. Okay. Is this working for everybody? Like, you can follow on with the code and kind of this thing? I haven't looked up very much, so I don't know if, okay. All right, I'm kind of actually doing pretty well on time, so I can slow down a little bit. We talked about GLSL and compiling them into SPIR-V. It turns out that this sample package has a bunch of utilities, which you could actually grab and use if you want for your own purposes. But one of the nice convenience functions in there is GLSL to SPIR-V. This is just a little helper function to take the actual text of the shader and compile it to SPIR-V. Mark, do you have the actual source code for the shader? Yeah, there it is. So we were kind of lazy, and we just stuck it in as a text string in the program, and we call that utility routine. It gives us back the binary stuff. So it just cuts down on the number of files lying around in the demo stuff. And with that helper function in place, it's real simple to create a shader module. You just have to tell it where what the code size is and point to the code that came back from that utility. John mentioned specialization. We're not doing any of that here, but here's where it would be if you were going to do it. And at this point, the shaders are ready to go. Another kind of attribute of this demo package, or the samples package, is sometimes we fill in things in the info data structure ahead of time and don't really use them until later. And that's an example of. This is a good example here. We'll use the shader stages pretty soon. Okay, frame buffers. Well, what the heck? We created a swap chain. Why do I need a frame buffer? Frame buffers are, they define the collections of like associating a render pass with attachments. So let me shrink this picture a little bit. It's probably better to get it on one screen. So in this case, we have two images in our swap chain, so we need a frame buffer for each one. And so this describes, okay, there's an attachment of color 0, and you can share the def buffer between the two images, between the two frame buffers. And then the render pass definition can, of course, be reused. And there's the single def buffer that's used for both. Okay, and then usual stuff here, we're going to make two frame buffers, and then we create each one, but we substitute we use the same attachment data structure. Where did it go? Oh, yeah. We put the def buffer into attachment 1, and attachment 0 gets its frame buffer depending on which of the, I'm sorry, it gets its image buffer from the swap chain depending on the index. So swap chain image count, there'll be a unique image for each image in the swap chain. And so now we have our frame buffers figured out. Okay, vertex buffer. Okay, we've been doing this for about 40 minutes, and here's the first time we actually talk about pixels and vertices and graphics and stuff. So this is kind of cool. We're going to pass just like GL, you're going to put the vertices into a vertex buffer object, and Mark's ahead of me and has the vertices on the screen there. If you're interested in just a little dumb exercises, it's a cube, and it's drawing 6 faces, so there's 12 triangles, and so 36 vertices, and they're all repeated, and the facet colors or the face colors are repeated as well. So obviously there's more efficient ways to represent that data, and if you wanted to do a Vulkan exercise for yourself, you might try doing that with indices and just having one color specified for each face, just as a little challenge. Vertex buffers are created in a very similar way to the uniform buffer, except that we say it's going to be a vertex buffer. And it's this kind of, once again, the same thing. You allocate the memory the same way, you map it, and then we mem copy it in, and then unmap it and bind it. So it's a very similar procedure. There's some additional things to fill in, which these bindings and attributes are going to be used later when we define the graphics pipeline. But since we happen to be staring at the vertex data now, we're just going to go ahead and fill it in. And so this just describes where the color data is and where the vertex data and the color data, what the stride is, and those details. Okay. Let's see, what am I trying to say here? So I guess this is just a little sneak peek ahead. When we go ahead and create the render pass, this is, we're going to go ahead and bind the vertex buffers into the render pass. So this will, this is what, when we start the drawing, this is how you find the vertex buffer, or how the GPU will find it. Okay. Mr. Pipeline, let's see if I can shrink this guy down a little bit too. Okay, the graphics pipeline has a lot of stuff in it, and we don't have to talk about all of it. There's a render pass and the frame buffers and our attachments. We have our shaders and the pipeline layout, and then we have a lot of pipeline state. So we're actually not going to talk too much about these states, because we're going to be setting these to pretty much simple default values, the default, the usual depth testing and depth buffer parameters. We're not going to multi-sample, color blend, we're not blending anything, rasterization is straightforward. So a lot of these will be just pretty boring default settings, just to give you a preview. Or a couple things to talk about. It was mentioned again a couple times this morning that the viewport and the scissors are often set up as dynamic states so that you don't have to rebuild the pipeline if the window size changes. So let's see, where's that done? Okay, someplace on the page we do that for vertex, for scissors, and I don't know where it is right now. It might be in the bigger code snippet. The pipeline vertex input state, this is what we set up on the previous page, what the bindings and attributes were for the vertex data. So that fills in that part of the pipeline. The assembly state says that we have a bunch of independent triangles, which is what this means. It tells you how to form the vertices into primitives. It tells the GPU how to do that. Pipeline rasterization, again, default. Okay, here's the pipeline viewport state. So this is where we're turning on the dynamic state enables. I forgot it was further down here. So we're adding to this list. We want the viewport and scissor states to be dynamic. Def stencil is pretty static, so that's set up, in the usual, compare and stencil operations. Pretty straightforward. And sample, just one bit. And then finally, we put it all together. And this is, again, classic Vulkan code. Just fill in all this stuff in the create info structure, and then pass that to create graphics pipelines. So we're almost done. Okay, so finally up to section 15. And by the way, if I haven't said it already, each page of these samples, each page of this tutorial has a corresponding standalone compilable sample program. So you can go into the sample program and find a program called 15-drawCube, and it's a complete program that will go ahead and draw the cube. Or you can go back to like page 6 of the tutorial and find the code that corresponds to that. Most of the programs don't do anything except the last one. Some might create windows and not much else, but so they don't do much when they run, but they're useful for putting on the debugger and playing around with them a little bit. Then, so one of the things you have to do is you have to wait for a swap chain buffer to become available. This is especially important if you're rendering in a loop all the time. In this program, which just draws one thing, you could argue it only needs one swap chain buffer anyway. Some implementations actually require that you have two, though, for a minimum. But in any case, there's a semaphore to help you determine when a swap chain image is available, and then you make this call to acquire the next one. And this says, okay, I'm going to wait here until I get the next available image that I can render into that's not being used by the display backend anymore. Like I said, the first time you do it, you're probably not going to wait very long. We go ahead and begin the render pass. So we insert a command. One thing that's missing here is the command buffer has already been opened, and it's in recording mode right now. So the first thing we put in is a begin render pass. Actually, I explained that here a little bit. And and this is where you set the clear values so that the frame buffer and the def buffer get cleared properly. We bind the pipeline, which we defined in the previous lesson. We bind the descriptor sets that we built a while ago. And you probably remember in the vertex buffer, that wasn't too long ago, so we go ahead and bind that. And then since we said the viewport and scissors are dynamic, we go ahead and set those with a command to set the viewport. And there's a similar one for scissors, which is very similar. And then finally, there's a draw call. And then we end the render pass. So the command buffer is still open at this point, I think. Yeah. And this is, again, we're discussing how to do the layout transitions here. But then we're pretty much done populating the command buffer. And then we go ahead and finish it off and take it out of recording mode. And then we go ahead and submit it. But to do that, we also need to create a fence so that we know when the GPU is finished rendering, because you need to know when the GPU is finished rendering so you can start the present operation. And that we accomplish with a fence so that we don't have to get the host machine too involved with that. So we go ahead and submit the queue. And then, we actually do wait for it. Yeah, so we do a wait for fences here for the GPU rendering to complete, and then we go ahead and present it to the display here. And at this point, ta-da, we get a cube on the screen. So that's the tutorial. Is there any questions, any part you'd like me to go over a little bit more detail? I'm a few minutes ahead of schedule, amazingly. Nope. Okay, we've got one here.
Could you talk a little bit more about binding things like vertex buffers, where the copies occur, what timeline they occur on, if there's any temporary memory that gets copied on the GPU timeline?
So the question, okay, so we have a microphone, so I don't have to repeat it, but just for my own understanding, you're wondering, when you bind a vertex buffer, if there are any additional copies going on?
Yeah, sort of, at what time is the data actually updated? And is it updated in like a staging buffer and then later actually updated in a GPU-specific heap?
I guess I'm not sure of the answer. My first response is to suggest it might really depend a lot on the driver and the implementation. Tobias might know the answer. Yeah.
I mean, I'm going to cover this a little bit in my synchronization talk in a minute anyway, but no, there's no staging going on. I'll explain exactly how that works, when I do my talk, but there's no staging going on. The only time you'd see a Vulkan implementation doing something like that is if it would have to work around some hardware bug. It's not intentional or intended by any of the specs, and doing so would be unnecessarily costly.
Okay, that's reasonable. So that kind of also points out, that there's not that much going on in the Vulkan drivers that you don't see. So you might expect a GL implementation might stage something, but in this case, you've written the vertices right to memory, and you're handing, via the descriptor, well, not the descriptor, but by doing the binding, you're handing a pointer to the pipeline right to the vertices. So the shader should be able to read the vertices straight out of memory. And I don't know, maybe in really weird cases, the driver might have to reformat or move some stuff around, but I don't think that's very common. It's just an array of vertices. The shader program should be able to manage just accessing it directly.